170 secret show right now because of
Tushar.
Yep.
I'll probably give him a live stream or go watch this in the office.
Okay.
Can you post the link in Slack?
Yeah. I'm about to start soon, but.
I'm not either. You gotta find me.
Yeah, but those people, they don't accept me. My people.
There's a difference.
I would buy you food. That's why they're just
Yeah, or people that don't have to study as much, you have to study as much. Or even if people around your level, that you guys yeah, I got
unless I
that.
have to. I study like 2 hours before these. Yeah, that's probably fun. Like if you look at my cheat sheet for 70, I totally deserve like
My cheat sheet usually has around 4 times on it.
Yeah, same. And mine is like shit.
I
I don't even understand the things on my cheat sheet.
Is everyone here for the computer vision workshop?
Yes.
Okay.
So what should we install?
Okay, so the way that I'm going to do this, because of prior experience with installing this stuff, is you don't have to install it, but you can log into the CSUA server, which I can give instructions for, and just use it on there, and I've already installed it. So is anyone here not a CSUA member? Okay, do you want to become a CSUA member? Jordan, do you want to, or you're not a, Ben, can you help them? Yeah.
Go to CSUA.
Yeah, if you never actually use your account, don't remember what you put for anything.
Do you know your username?
I've never used my account.
That's okay. Right, I'll just look you up right now because there's not that many people here. Wait, this works, right? Yeah, okay. So, who has SSH? Who has SSH into the CSUA server before? Okay, then I'll give detailed instructions. Let me just get Jordan his account. Definitely using RSA, right? What is your Berkeley Calnet ID?
Jordan Hart.
Okay.
JRT.
Okay.
Once it loads. Oh, that didn't work. Okay, your username is Chessmaster. Do you need me to reset your password?
Sure.
Okay.
Do not violate the law. It's really hard to do.
Uh-oh.
I'll just try to guess.
Do you know it?
I can.
Okay, try SSHing into csua.berkeley.edu and see if you get in.
Okay, that's where
Wait.
Did you get in?
Yeah.
Okay. So I'll now walk you guys through the process of is this big enough for everyone?
Bigger.
Bigger? Okay. How's that? Good? Okay. So does everyone now know their CSUA login information?
I was trying to check what. I just used
Okay.
thing to go with it.
So the way you log in is does anyone here use a Mac?
Yeah.
Okay. And then who uses Windows? What version of Windows?
10.
What about you?
Arch.
Okay. What about you? Okay. Do you all know how to start up whatever SSH client you normally use to get into like the Hive machines and stuff for classes? Okay. So open the terminal app and then since you have a Mac, it'll be the exact same command that I'm showing up here.
Okay. But with my name.
With your name, yes. So this is the command. So Ben, you're logged in to
Yes,
the
I'm
server?
logged in.
Okay. Jordan, you're in?
Yeah.
Okay, Blair's you're in?
Okay.
Yannon?
I'm trying to find an outlet with power.
Oh. It looks like there's I can't tell, but there's one on the front row that
Yeah,
might
they're
be.
all, like, not working.
Oh.
Just connected to the front.
If you sit in the front row, you might be able to plug it in here.
Okay.
His reaches, but I don't know how long your cord is.
That's long enough.
Yeah, if you sit next to Ben, you might be able to. Okay. Anyone not in yet, other than Yannon? What's your name? Okay, and what's your name in the back? Were you able to log in? Okay. Yeah, there's not that many people, so yeah. 100 people put interested on Facebook, but I guess not too many people actually.
I think about any buzzword, you'll get at least 50.
Yeah.
Yeah, computer vision.
You put free food, then there'll actually be 50.
Yeah.
Yeah. So it'll ask you for your password, and then you just eventually you'll get a prompt. So everyone's here then, except for Yannon. So we will come back to this. I just wanted to get you guys logged in first to make sure it all works. So what do you guys know about computer vision? Anything? Any ideas? Yep.
It's for like image recognition kind of stuff.
Yeah, like object recognition, those kinds of things. Anyone done any computer vision stuff before, or are you all completely new to it?
I'm too.
Okay. What have you tried to use?
What do you mean use?
Like what kinds of algorithms and
Oh, I'm still in like the exploratory phase.
Okay, so I'll start with the basics. So basically, computer vision is a very challenging thing for computers to do. What you want them to be able to do is you give them an array of numbers which represent an image, and them to figure out what objects are in the image, just like your human eyes do. And while it's very easy for us to do this just by looking at something because our brains are specifically designed to do that, computers are definitely not designed to do that, and therefore the algorithms to find things in images are very complicated. Luckily, after decades of computer vision research, all of the major algorithms that are available have been distilled into libraries that you can just use and call their functions, and some of our professors here at Berkeley have made some of these algorithms, and they're now just packaged into a convenient library. So I won't go into the implementation of most of those because they're very complicated and I don't understand half of them either. But to use the basic computer vision functionality that can be done with one of these libraries. So just to get started, the way an image is represented in a computer is by a matrix, and rather than just one matrix, because we want to have color images, we'll want to have 3 matrices, all the same size, one red, one green, and one blue channel, and they combine together to make a color image. And so when we work with images, then we will see them as matrices, and these matrices will have 3 dimensions to it. So normally you have like a 1920 by 1080 image. We'll call this a 1920 by 1080 by 3. So that way you have 3 matrices stacked on top of each other, basically. So once you have an image, then now you want to start doing operations to it. So what's the simplest operations you can do to a number? Yeah, so arithmetic operations. So one big arithmetic operation that people want to do with images especially is something called thresholding. So in each of these matrices that we're going to be working with, all of the values are 8 bits. So what's the range of that then? The range of the values for an 8-bit number? Yeah, so you're both correct. One's signed and one's unsigned. So in this case, we'll just call them unsigned. And from 0 to 255, where 0 means black and 255 means the maximum intensity of whatever channel you have. So if it's 255 in the red channel, that means you're full red. If it's 255 in both the red and blue channels, then it's going to be what color? Purple, yes. Yeah, so basically you just combine these 3 colors in whatever way you want, and it goes from 0 to 255. So now the first operation you might want to do on this is thresholding, where you'll say, let's say in a black and white image even, so not worrying about the colors, then what parts of the image are bright, what parts aren't. So we can say, let's threshold on 128. So any pixels that are more bright than 128, we're going to turn them to 255, full brightness. They're all white. Everything that's darker than 128, we're going to make them completely black, all zeros. So that way it'll basically make a binary image in which everything is either on or off, and that specifies what met our thresholding criteria. Everyone makes sense of that?
So you'll go through the matrix, which is full of numbers.
Yeah.
And you're gonna say like, if it's greater than some value, make it super bright.
Yeah, maximum brightness.
And if it's less than a certain value, it's super bright.
Yes.
Okay.
So that's what you do. You basically make a triple for loop over the width, the height, and the number of channels, and just check every single number. That's not exactly how it's implemented for speed reasons, but that's how you can think of it. So can anyone think of useful reasons why you would want to do this?
Detect what is going on, what's the background, and what's like the actual thing you want to see.
Okay, so if you were trying to distinguish the background from the foreground, then how would you use thresholding to figure out what's in the back and what's in the front? Like, what would you?
If it's like against a white background, then you see everything set to 255 for everything.
Yeah, so that's a great example that if you have an image in which you know the background is white and the stuff that you want to look at is not, then you can do the opposite threshold, because thresholding does not have to be greater than or equal to. It can also be less than or equal to. You can say if something is less than or equal to, let's say 250, so that's pretty high up, then it's something we are actually looking for. If it's above 250, it's probably the white background because it's really, really bright. Does that make sense? You can stop me whenever you want with questions. There's only like 6 people, so this is really like a seminar, not really a big lecture. So if you use those kinds of thresholding techniques, you can get pretty far just in this RGB system. But a little bit later, I'll introduce a different type of system that's much more useful for thresholding. But first, let's just dive into an example. So I am going to copy an image onto the server so that everyone can just access the same one. make this smaller so I can see it for a second. Could you try to see if you can less this file? This.
From your home folder?
Yeah, from my home folder, just to make sure that the permissions are right.
So what are we doing? LS. So LS dash L.
No, just I'm just asking Jordan to. I just needed one person to check that it's actually accessible to make sure that I set the permissions right. But did it work?
I accidentally tabbed all and it showed like all
Oh.
the users. Slash T. Okay. And you said
81 inches dot JPG.
okay, I definitely got lesser folder. Let me see if I can do anything to the image.
81 inches dot JPG.
81.
Okay, you won't be able to access it. But
I
I need
can't
to.
see anything in our folder. Or can't do anything to any file, that file in it.
Okay, let me give world access to my.
You just make a new folder for sharing. The demo.
Everything in my home directory is for demos.
No.
That's interesting.
What was that?
It's an interesting way to set stuff up.
To hide things or not hide things?
I just saying, like, having everything in your home directory for sharing. If you're doing a lot of those, I guess.
Yeah, I don't.
Okay, now
I don't do
access.
much else. Okay, so you can less the file.
I just cabbed it.
Okay, yeah, that works. All right, so I'll just show you what the image looks like. This is a basketball hoop from the first robotics competition in 2012 when I was a freshman in high school, and I wrote a bunch of computer vision code for this. So what we had was a robot that had a basketball shooter that took in an RPM, and it set how fast the shooter was spinning, and it would shoot the basketball. But we needed to know how far away the hoop was and at what angle it was at so that we could position the robot correctly. And in order to do this, we needed to, in an autonomous mode, we would have to be able to do this completely programmatically and not with a human, any human intervention. So, can anyone think of like what kind of information we would need in order to find the distance to this? Note that it's in the title, in this case only because this is a calibration image. I know I measured by hand that this is 81 inches away, but if we wanted to do this in a program, what would you need?
First, I guess you need to identify what is the hoop.
Yes, so conveniently, because this is a high school competition, they didn't make us actually find a hoop. They put this bright rectangle on it that has retroreflective tape, so when you shoot light at it, it comes back directly at you, very, very bright. So conveniently, there's a rectangle right there. So all we want to do is find the rectangle, right? But if we find the rectangle, how do we know how big it is? What do I mean to say? So if we're like closer to it, it's big. If we're far from it, it's small. So how would we figure out how far away we are exactly?
Just by the sides of the rectangle.
Yes, so you need to know how big it is in real life, and then you can compare it to how big it is in here and turn that into a physical distance. So I'm not sure exactly how long, what the pacing is going to be of this workshop. It depends on you guys and how you want me to do it. But if we get time at the end, then we will calculate the distance to this and hopefully get 81 inches. Otherwise, all of the code to do this is going to be online because I did this already in high school that I did this challenge. I'll just be walking through how this was done. So back to the terminal. If you run IPython, let me go back to a big text. So if you run IPython, it'll give you a fancy Python interpreter that just has some nice syntax highlighting and tab completion. And the library that we want is CV2. This is OpenCV, which stands for Open Computer Vision. It's an open source library that just has a lot of functions for computer vision tasks, and it's version 2. So the Python module is CV2.
Side comment, have you ever thought of just hosting an iPad notebook for all these demos?
Yes, but that would make it public on the CSUA server, which may be dangerous.
You can make it have a ConNet ID to sign in.
It's too complicated.
Okay.
So are you having trouble?
Oh, no, it's all good now. Okay.
Okay, so everyone got this imported successfully? So, okay, that means everyone's environments are...
We're having problems.
Okay, so
This is an issue.
are you SSH'd into the server already?
Yeah.
This is no module named CV2.
Okay, let me take a look. Just so I know.
Okay, yeah, let's do this. Just, I guess, just try to do like Python, but we still have to install Python too.
But this is on Soda,
But I
so
just like to, okay, so
you don't need to do Python 3,
Well,
just do IPython.
IPython?
Yeah, at the terminal. So close
Oh,
out
okay.
of Python first. Oops. And I just type IPython.
Okay, it's like this.
Yeah, and then do
Okay.
import CV2.
Right.
So that's exactly how I did that up there. I set up the environment for you guys beforehand because that's usually takes up more than half the workshop otherwise. So if we can get this, then we're further than most workshops are by this point. So, all right. So now that we have the OpenCV library ready, we can do the first thing, which would be to read in the image so that will be in my home directory. So you'll just need to copy this path exactly. Home tpankaj 81 inches .jpg and save it to, I don't know, hoop. So this will just load the image in. Anyone need more time?
Or maybe CV2. Oh, CV2.
Right, everyone got it to this point? So now that you have the image loaded, let's take a look at what it looks like. It's a giant list of numbers. So as expected, our image is just lots of numbers. It's a very, very big array. If we
Wait, that's the compass.
this is a class in Python, so we can do hoop.shape and see how big it is. So it's a, I guess this one is in height, comma, width, comma, channels. So it's 640 by 480. That's the size of the image if you go width by height, and then 3 channels. So that's the image that I showed, not that, this image. So now we have it loaded, and it's just a bunch of numbers. So now we can write programs to do whatever we want to it. Now that it's no longer a thing you're looking at, but just a bunch of numbers, your computer knows how to play with numbers. So the first thing that we can try doing is, let's see. So I usually refer to the OpenCV documentation to make sure that things are correct. So now we've loaded the image already. Let's look at threshold. So there's an image transformation list of functions in here. Let me find, where is it? All right. So what this function does is applies a fixed level threshold to each array element. So it takes in a matrix and it will, let's look at the Python version, not the C++ version. It takes in an image, it takes the threshold value, which is the value that we care about it being less than or greater. Let's see, here. So this one tells you whether it's less than or greater than. So thresh binary means that the destination is going to be max val, which is one of the arguments. if that array element is greater than the thresh, whereas this one is going to make it 0 if it's greater than the thresh. So does that make sense so far? Anyone confused?
So
Okay.
the top one would be painting it white versus like the bottom one's painting it black.
Yes, exactly. So now we will just need to give it an image, give it what we want to make our threshold, and then give it what we want it to paint it as. It'll paint it. It does not have to paint it white. We can make it paint it red or paint it green or whatever we want. That's why it lets you specify max val. I would usually just make it white for ease of computations. There's one problem here though. How do we know what to threshold on? If we're trying to find this, the rectangle, what's very obvious about this rectangle when you take?
Bordered by black.
So, okay, so it's bordered by black.
And also it's very light in the background isn't light.
Yes, so the purpose of the black tape is actually just to provide a contrast. The real thing that we want to search for is not the black, because it's regular duct tape, but the actual white part, because that's retroreflective tape, which is a special kind of tape that when you shine a light at it, rather than the light scattering everywhere when it bounces off, it will bounce directly at you. And the light, and there's a light, as you can see, there's a green shadow over here. There's a green light right next to the camera pointing at this thing. So we can see the green very, very clearly. Even if it's not terribly obvious by looking at the picture that it's green, if you actually zoomed in all the way to this thing, it would just be completely green. So what could we do then if we have this?
We should look for green stuff.
If we can like threshold the second value in the array to see if it's greater than 220 or some value like that.
Yeah, we could do that. So what happens though if there's a white thing right next to this? So this is green, but what if there's a white thing right next to it that's like some lamp that someone has put next to here? Like this is in a classroom, so
And the first and the third values are going to be very high.
yeah.
Versus if it's just green, it's going to be close to 0.
So it could be close to 0 or it might not be, because if you notice this isn't a fully green. Like if you look up if you just look up what pure green color would be expected to look like, it would be like this color, like really dark green. That's what 255 on green means, whereas there's all sorts of other shades of green that are not the same on the other values. So this is somewhat of a trick question, because there's actually a better way to do this called HSV. So right now we're in RGB domain. Has anyone here not taken linear algebra? Okay, so I won't use too heavy of linear algebra terms, but I'll try to also incorporate those for those who do understand all of linear algebra concepts. So basically what we have right now is an RGB color space. So that means that every pixel is a point in RGB space where you have 3 axes, one is R, one is G, and one is B, and for every possible color it's a point in that space. Does that make sense to everyone? Anyone confused about that? Okay. So now that if you have a point in RGB space, there's no reason that you have to use RG and B to access this, right? I can rotate the axes and say, okay, well now I'm gonna get this point in terms of these coordinates. So for example, there's polar coordinates and there's rectangular coordinates in like math, where you can represent a point either as x comma y or r comma theta. So we can do something similar where rather than representing it as R, G, and B, we're going to figure out what the same color is but in HSV. So HSV stands for hue, saturation, and value. The value is just the black and white version of the color. So that just tells you how bright is it. Because if you take a color image and you make it into black and white, all it's telling you is how bright things are, because you lost all the color information. You only know this is this bright, this is that bright, that's all. But in order to reconstruct the full color, you can't just have that. You need to have more information. So there's 2 more, hue and saturation. Saturation I won't go into, but hue is really important. Hue is basically what color is it, not in terms of like light green versus dark green. That's what saturation is about mainly. But this is in terms of, is it green versus red versus like purple. So it'll tell you the difference between all of that. And if you really care about what color something is, you'll want to take it into the HSV domain, not in the RGB domain, because RGB gives it to you in terms of how much green is it, how much red is it, how much blue is it. But that's not that helpful. You want to know what color is it. That's a very slightly different question. So if you transform something into the HSV domain, then now you can suddenly say, well, I know that in HSV, green is from like 60 to 80-ish. Those are the green values. Then I can just threshold on the bottom and threshold on the top, and now I have a range that's only those green values. Does that make sense? Okay, so now I will refer to my own code from freshman year because I don't remember the exact syntax of everything. And this is in C++, not in Python, but I will show you the Python commands. Okay. So the first thing that we have to do is actually just convert from RGB to HSV. So there's a convenient command in OpenCV to do that called convert color. Converts an image from one color space to another, and that's exactly what we want to do. So in my code, I did that somewhere. Yeah, convert color RGB to HSV. So if you notice, you literally just tell it, I want RGB to be changed to HSV, and it does it for you. So let's translate that into something that we can actually do here. So back over here, we can say hoop HSV is convert color. And then let's see what the arguments are. So we want the source and the color space conversion code. So the source is just hoop, and the color space conversion is, it may be different in Python, so I just want to check. This just gives you all the math in case you actually care. I don't. Here it is. Okay. So CV, actually I believe in OpenCV 2 it's now just RGB. CV underscore RGB 2. Okay, I guess that doesn't exist either. RGB to HSV. So it needs to be this thing. Okay, it's not finding it. Let me just figure out what it's called. Anticipate it being different, but let's did someone just come in? Okay. Have you guys?
Isn't it color underscore RGB or
What's it?
it's calling it BGR?
There's
CV2 dot
CV
dot color
dot color.
underscore
Oh, okay.
BGR.
RGB to All right, thanks. So let's try that again. So hoop HSV is going to be cv2.convertColor hoop, and then cv2.color RGB to HSV. Amazingly, that doesn't match the documentation, but that's all right. So now we have hoop HSV. Is everyone at this point yet, or should I wait a little bit longer? All right, can you put a thumbs up when you're done, just so I know? Which one's not defined? Oh, so what did you name it when you loaded the image like this? Using the hoop equals cv2.imread. Did you get it working?
Yeah.
Okay, so now from our perspective right now, it doesn't look like much has happened, and it hasn't really. It's just changed the numbers into another meaning. But now we have it in, what's it called, in HSV form. So note that the shape of this is still how we expected. 640 by 480, 3 channels. Nothing has changed except that we've changed the, in linear algebra terms, the basis vectors for the point, or just rotated the axes. So what we'll now want to do is isolate the hue, because we'll probably want to care most about the hue and not about the other stuff, because we really care about the green. So hopefully this works. Yes. Okay. So what this does, if you're not familiar with it, is it uses Python's slicing. Has anyone not worked with slicing before? Okay. Has anyone here not taken 61A? Just everyone's taken it? Okay. So then, yeah, so this will pick out the first channel. Hoop hue.shape. Is it the 0th channel?
Oh,
So I did all of the rows, all of the columns, and the 0th channel. And so now we have the 0th channel, and it's 640 by 480. So now if you print this, what did I do? Now if you print this, it'll just be a single matrix. And now this is much simpler, much easier to work with. We don't have channels anymore, just a single matrix, a 2D array. So now that we have this, we can actually threshold. Where's the, oh, God. At this point, is anyone confused or lost or doesn't know what we're doing or anything? Any questions? Okay. And could you raise your hand right now if you think I'm moving too slowly? Too fast? Okay, so now we can go to thresholding. Yep.
When you work like this, where you're just like throwing in code, like how do you verify that things are actually happening?
So we'll print it once we actually get a picture.
So you have to like wait until the end.
No, we can actually show one right now. It's just that if you have a Windows machine, it'll be a little bit annoying. If you have a Mac, then let's. All right, if you have a Mac, then you can, or Linux, then you can SSH like this instead, and it'll let you open Windows up. If you have Windows, then it's much harder to get that, and so you might just want to look off your neighbor. Let me make sure that. Oh. And make sure that. I just want to make sure that I just test it and make sure that I did it right. Let's see, 2. Okay, that didn't work. Maybe I will. Okay, that still didn't work. So it's a little bit difficult to get the images to show. What you could do is dump out the image to a file and then copy it over to your machine, and then you can easily see it rather than bothering with this. So yeah, I tried to do that, but I guess it's gonna be a bit of a headache. So once we have it thresholded, I will go through the instructions to actually copy it over so that you can see what it looks like, because at that point we'll have some interesting results. So far we're just going to be doing some grunt work on just getting it. Alright, so let me catch up to hoop HSV hoop hue. Alright, so now we'll want to actually threshold it. And because this thing only does less than or equal to and greater than or equal to, we'll want to actually do this with both the lower and the upper threshold bounds separately and AND them together. And so if you, the reason you would AND them together is that first you would check whether something is between 0 and x, and then you would check if something is between y and 255. Well, really between, 0 and x and y and 255, and then you want to take the stuff that's not that, so you would go into the middle part. Does that make sense? Okay, so what I do here is just do it in 2 steps. It might be a bit small, but I'll put it into Python soon. So we'll do it in 2 steps and then AND them together and dump out the image so we can see what we did. Where's the threshold? You don't have to have such long names as I do, but I prefer to make things clear, so let's see. So I'll create the command and then I'll keep it on my terminal for a minute so you guys can see it. Thresh. Should probably figure out what the threshold is.
I think it's between like 60 and 180.
Is that what I have? Ah. I do have it somewhere here. 0 and 80. In OpenCV, the hue is between 0 and 255, and in standard non-computer related stuff, hue is often in degrees, between 0 and 180, so it's a bit weird.
I'm just looking at Wikipedia.
Yeah, so I had to convert those values into what OpenCV's range is.
Okay.
So the bottom value is 0, and the top value is, so in that case we don't even need to AND it. We'll just want to do 1. Where's this? Yeah, 0 and 80. So the upper threshold then is what? So in that case we don't even need to AND anything because one of the bounds is 0, and because of that we don't actually need to threshold anything there. So we want hue and 80, and then oh, oops. There's binary inf. Yes. Alright, so this is the command in line 7 that I ran. So what this is doing is that it's going to take the hoop hue matrix, and it's going to say that the upper bound of something that we want to keep is going to be 80. So anything 0 to 80 we're going to keep, and for the stuff that we're keeping we're going to set it to 255. We could have set it to whatever we want. Everything else will be set to 0, but the values that fall within the range that we want to threshold on are going to be set to 255. And thresh binary inf just sets whether we want it to be less than or equal to or greater than or equal to. In this case we want less than or equal to, whereas the standard is greater than, so that's why it's inf for inverse. Anyone need more time to run this command? Alright, so now let's see what we have. The way that we read the image in was like this, IamRead. So the way that we're going to dump it out is command IamWrite. Let's see what the arguments for IamWrite are, just to make sure I don't mess up. So one tip for this is get used to being able to look at this really big documentation and find what you need quickly, because then even if you're in the middle of giving a talk on it, you can still find the information you need very quickly without having to memorize literally every command, because there's so many commands in OpenCV. Alright, so file name, comma, image. So that's it. You just need to do thresh. Oh, what did I do?
Isn't it just hoop.jpg?
What's hoop.jpg?
Isn't that just the image? Or
What do you mean?
like the first command or the first parameter?
Oh, the first argument. So you're saying instead of doing hue thresh.jpg?
Well, that's just a file name, so you can put anything you want there.
Yeah.
So note that this image is mostly zeros. That's what's expected. We only wanted the rectangle out. So let's see what happened here. Yeah, these commands are slightly different in Python than in C++, the language I wrote that in, and I wanted to make it Python so it's more accessible to everyone. I mean, how many of you in here know C++? Okay, yeah, that's why I wanted to make sure it's in Python, but that also causes a bit of compatibility issues. Conveniently, there's always Google. Yeah, it's complaining that it's all zeros and ones or zeros and 255s and not in the type of numbers that it wants. Alright then. Only 8-bit. Can you save with this function? So, let's see what happened then. That's why. It returned more than just the image, so I'm just being dumb. It should be the second value because it returned an array of, or a tuple of 80, which is the threshold, and then the actual image in the next element. So we actually only wanted that, so we can run this. I'll leave it up for a second before I run it. So we can run this command, and it'll overwrite the name hue thresh with the actual image. This was a tuple that had more than what we wanted.
So basically,
We're getting the
second.
the second element, or counting from 0, the first element of the tuple.
Okay.
Because it returned a tuple, and I did not realize that because there's no tuples in C++. So, anyone need more time to run this command? Alright, so now if we run I am right, then it'll return true, showing that it worked. So, just to... Yeah. So this is now the command to write the image to the file, and it'll return true, indicating a success. Anyone need more time on the I am right command? No? Okay. So in that case, we'll now copy it over to our own machines so that we can see it. So if you ls in your home directory, you should see this hoop hue thresh.jpg is now there.
How you doing on the
Just ls.
server?
Yeah, your home directory on the server. So, does everyone have this file? Raise your hand if you don't, and I can help you with that. Alright, so now if you log out of the SSH session, and I don't know how many of you have used SCP before. Could you raise your hand if you know how to use SCP? Okay, so I'll show you how to use it then. SCP is secure copy, so using the same system as SSH, you can copy a file between two machines, not just use a terminal on the other machine. So if I just say SCP and then my username at CSUA.berkeley, colon, and then the file name I want, space, dot, what that means is it'll tell the computer, go to csua.berkeley.edu, log in with my username, find the file in my home directory hoop-hue-thresh.jpg, and save it to my current directory in my local machine, so your laptop. And when you do this, then it'll ask for your password and type your password, and it copies. And it gives you the stats as it's copying, but this is a tiny file.
Do you need the dot after the JPEG?
JPEG space dot, yes.
What does that do?
Dot means the current working directory, so on your local machine, it's telling your computer, I want you to store it where I currently am sitting. And I'm currently sitting at /home/the shar, which is my home directory on this laptop.
Oh, it's saying keep. Oh, that's not right. So I just want to copy. Okay.
So everyone got it copied over? Thumbs up when you have it. Okay. Ben?
Oh, I got it.
Okay. And Blair?
I think I messed up with saving it.
Okay. Do you want me to take a look, or Ben? Do you?
I'll take a look.
Okay. So if you open the image file that you get, it should look something like this. Actually, it should look exactly like this because we all did the same thing. And luckily computers are deterministic. So I just opened it in my image viewer full screen so that we can see it really big. This is what it looks like. It's a binary image as we expected, only black and white. And nicely the rectangle is very visible, but unfortunately there's some annoying background noise. And
Where do we find this?
In your home directory, probably wherever you started the. Yeah.
To the directory.
Yeah. So over there. Yeah. We just copied it over to make it easier to open the file and view it. Yeah.
Weird.
So were you able to SCP it over?
Yeah, it seems like it worked.
Oh. So. Where were you? What directory were you in when you ran that command? The same one.
Yeah.
Where did you run it? Did you run it on Soda or did you run it on? So. You ran it on the
so I should
server,
just
so
ask it.
you should run it directly on this machine, and because what that did was just copy it from the server to the
Okay.
server.
Okay.
You can just copy and paste that command. It'll copy it to your local machine, and yeah, so everyone who has that open should have the same image that's up there. All right, so we have about 50 minutes left, so about half the time left, and because we're not, so if I go through all of the functions to get everything all the way to the distance, we probably will run out of time and not make it to the end. Alternatively, I can explain each step abstractly rather than actually going through the whole step, and in that case, we will definitely finish in time, but you guys won't be able to see every step in Python. Which one would you prefer?
Or the wrong one.
Yeah, so Ari and Yanin, so right now we have about 50 minutes left, about half the workshop time, and so we've gotten this far and shown a thresholded image, but we still have a bunch of different types of functions to cover before we actually get to finding the final rectangle and getting the distance. So if I walk you through every step of the way, then we will definitely not finish, but you'll see for the steps that we do get through in the next 50 minutes, you'll see in detail how to do it. Alternatively, I can explain each step abstractly so that you understand the computer vision concepts behind it, and you can refer to the code that I have online later to see exactly how to implement it. So which one would you prefer? Would you prefer the first one in which I walk you through all of it? Could you raise your hand? Just raise your hand for the first method. So okay, yeah, and then for the method in which I do each of the concepts abstractly. Okay, so I'll do the concepts abstractly. You can all email me or talk to me during my CSUA office hours or any other time, and I can in great detail go through every single step of the process, but and in Python with you. But for this workshop, since the majority seems to want the method in which I will just abstractly talk about each one, that's what I'll do for now. Does that sound good with everyone? Okay, and I'll put my contact information up at the end so that you can email me, and you can find my CSUA office hours on the website, and come in and I can show you in great detail. Okay, so just to recap where we are, we now have a thresholded image, this one that I've been showing, in which we've mostly isolated the rectangle from quite a bit of the background noise. Not all of it, but at least now there's a pretty clear-cut difference between the rectangle and everything else. So the problem with this is that that we don't yet have a box around the rectangle that we can say these are the actual coordinates of the rectangle. All we have is a bunch of zeros and 255s. So that's still not exactly what we want. So what would be a good next step, do you think? Just throw out any guesses and we'll see if what your intuition is on this. What was that? So how would you do that? Or like what would be one?
I guess like check the edges.
Check the edges. That's exactly what it is. So so now what we've done is thresholding. The next step is edge detection. So we want to find the edges around all of this stuff and make it so that rather than rather than having everything filled in, we want only the edges. So what edges do we care about? There's two of them in here.
Inner edge of the white thing, the outer edge of the white thing?
Yes. So
Or out of the box.
okay, I guess I must have done this without. There we go. So we want to be able to see this box right here and this box right here, the really big one around the whole thing. Those are our two rectangles that we want to find, and they're concentric and have the same aspect ratio, which means the ratio of width to height. They have all the similar properties, but we want to find both of them, and those are the only edges we care about. Everything else is garbage. So a professor here at Berkeley named John Canny invented an algorithm called Canny edge detection. Well, I don't think he called it Canny, but it's called Canny edge detection, and it takes any image and it'll find the edges in it. So we could have just found the edges in the original image, but a problem with that is that there's still tons of noise. So we did a pretty good job of already narrowing it down to really what we want. And now in this thing, if you look for rectangles, there's not that much you could find. You could find this. You maybe might get this one on accident. That's not too bad. There's way more noise in the image than that, and we filtered most of it out. So I'll show you just the Wikipedia picture for Canny edge detection, so that, since I won't be going through it directly, but here's an example. So here's a picture of some machine part, and here's the edge detected version. It's very clean. So it just,
Damn good.
it's very, very good. It finds the edges of everything. There's a couple specks here and there, but you know, it found most of the edges very nicely.
How does this compare to like Sobel or Pruitt edge detection?
To Sobel?
Yeah.
I've never heard of that actually.
I was like doing a little research for like a separate project and it came.
Sobel?
Yeah, Sobel edge detection. SOBEL.
Oh, right. Well, so let's see what that is. Ah, okay. They're very similar.
Okay.
This is the same image actually. So it's a little bit more detailed.
Okay.
And this is I can show them right one after the other. This is the Sobel and this is the Canny. So
Okay.
this may be preferable in other applications, but in this particular one, since we really want to find the points on that rectangle, this is better for our purposes. Yep, what was that?
So you can specify like how big of a contrast that is required to count as an edge.
Yes, exactly. So Canny has a couple of parameters. You can say how aggressively you want it to search for edges. So if you are really desperate to find an edge and you know it's going to be really hard, you can say like consider almost anything an edge, and it'll just add it as an edge. But if you have too many edges and you're trying to trim them down, and you're pretty sure that it's going to find your edge, even if it's really careful about what edges it counts, then you can do something that with a lower aggressiveness, and it'll maybe come out with something like this. If you put it on maximum aggressiveness, this image would be really messy because it would detect like everything as an edge. The entire image would just be like white. So it can go very, very aggressive, and that's usually not what you want. And the way you would find this in classical computer vision is just by trying values and seeing for your application what works the best. So does everyone understand how edge detection works? Any questions on that or confusion? Okay. So now that we have an image, yeah?
Are there edge detectors that work better?
There are many edge detection algorithms, so you could exhaustively try like dozens of them and see which one works the best for this. For this case, Canny edge detection is the only one that I tried actually when I was making this system, and it worked pretty well. So at that point, there's no real need to look at other possibilities. That I didn't actually know about the Sobel version, but they all do similar things. Well, they'll make edges around objects, and they'll have different aggressiveness parameters. Alright, so now that we have this, if you did this on this image, what it would do is basically draw a white line here, and a white line here in the inner one, and then some random garbage over here. But even now, even like this, it's still just white dots on an image. That's not what we want, right? We want actual numbers. So these are, yeah, they'll be like pixel values, but that's not going to be like, here are the 4 points of the rectangle. So what could we do now that we have a rectangle that's made of just the perimeter in the image, and none of that giant, like none of this is still there, it's only the edges. What could we do now? Any ideas?
Should we calculate the shape?
We could do something like that, yeah. So now that at this point, and this isn't what this image is obviously, but once we edge detect this, we're gonna have mostly only the rectangles left, and not even the inside of the rectangle. It's only the actual rectangle lines with a very thin 1 pixel line drawn as 1 pixel width line drawn all the way around the rectangle. So now that we
Try to find a ratio which would make them height.
Yes, but we don't yet have the position of the rectangle in the image. So there's something now called contour detection, where now that we have the edges, we want to detect contours, and the only difference between edges and contours is edges are white dots drawn on an image, and contours are, oh, this point is at 45, 28. This point is at 45, 45. Something like that. It'll give you actual numbers. It'll say these are the edges of the rectangle. So maybe I can.
So like detects the lines versus.
Yeah. So maybe I can draw a quick example. So if this is our image, and we have this rectangle here, it's going to be this really thin line in here, like that. But that's just an image here, and all this will look like is this big matrix in which it's all 0, 0, 0, 0, 0, 0, big 0 here, 0 there, and then like a 255 here, 255 here, 255 here, big zeros inside. That's what it'll look like, and it'll be a rectangle of 255s. And now we want to find that rectangle of 255s inside the image. Does that make sense to everyone? So these are the same thing. What contour detection will do is, rather than give you this, it'll give you, so we'll give you an array in which you have, so let's designate this point as 10, 10, just because, and this one 20, 10, and this one 20, 20. So in this case it's actually a square, but oh well. Now what the contour will be is 10, 10, 10, 11, 10, 12, all the way to 10, 20, and 11, 10, 11 or 12, 10, all the way to 20, 10, and it'll have basically all of the possible points, every single pixel value. It'll just read them all out and tell you what their coordinates are. So that's pretty helpful. Now at least we have the numbers of where the rectangle is located. So that's a contour. Does that make sense to everyone so far?
Go a little bit more into that, like.
Yeah.
So just where there's a white space it reads.
Yeah, so basically the way you could implement this is you could go pixel by pixel through the whole thing and say, and this, it's much more complicated than this to actually make sure that it's a real contour and not something not some noise, but you can go through it and say, okay, here's a white pixel, right? So let's add the coordinates of this pixel to my list. There's another white pixel, let's add that one. Keep adding, oh, this isn't white anymore, let's go over here. Well, there's more white pixels, let's keep adding all of these white pixels to my list. And now, instead of having an image of zeros and 255s, I have a list of, these are all of the points on this rectangle.
Okay, so it's just a list of
Of a dot,
positive.
of a, huge number of points. Yeah. So it'll be a lot of points, but that's all right. I mean, this is on a computer, so we don't care if it's a little bit unwieldy. So does anyone have any more questions about contours? And this is the terminology used by OpenCV, because I'm specifically teaching you guys how to do these things with OpenCV. Other libraries might have different terminology, but I'll just use the ones consistent with the documentation for OpenCV. So if you guys go and read the documentation later and want to use this, then these terms will be familiar. So, yep.
Do you take non-linear contours?
Yes, it doesn't have to be a linear. So a contour just means any set of points that forms a shape, a closed shape. So if I had this in my image, or like that, it'll detect those. Any of those kinds of weird shapes, it'll detect them all.
So fitting a function to a contour is a different.
Yes. So now we have not fit a function to it. We've only gotten the weird shape. And of course in this one it won't be a perfect rectangle, it'll be a little bit messy. But now at this point there's another, so we've found the contours. The next thing that we want to do is find a polygon. So that's fitting an actual function to this thing. So now we have a bunch of points, a list of all the numbers here, this and this, that tells us what are the points along this rectangle. And of course we'll do this the same thing for the internal rectangle. Finding one rectangle versus the other is no different. They'll just show up as two separate contours. But let's focus on one contour. Now that you have all of these points, you want to fit a function to it, and you want to fit a polygon. So conveniently OpenCV has a polygon fitting function called approxPolyDP. I guess I looked this up. DP are the initials of the people who invented the algorithm. I think they're from Berkeley also. Yeah, so they made an approximate polygon function that takes a contour and it gives you a polygon. Or they made this algorithm, and OpenCV implemented it as approxPolyDP so that you can just call it. Once you call it, it'll approximate it as a polygon. And the best approximation that it gives you is going to be, rather than having all of these points, it's going to give you just this. 10, 10, 10, 20, 20, 10, 20, 20. And it won't necessarily be perfect because there's always noise in the image, but it'll give you something close to that. The polygon approximation, unless it's not a rectangle, it'll return 4 points, because it's going to figure out that the best approximation to this as a polygon is a rectangle. No other polygon is going to, or at least a quadrilateral, 4 points, not like 5 or 6 or 20 points or 2 points. It's, yep.
So then we see there's a rectangle within a rectangle. We know that's the one.
Yes, so now we haven't found a rectangle yet, right? We know that we have a quadrilateral. There's a couple of more weird checks that we have to do, because what if this guy over here was detected as some weird shaped quadrilateral? Like, we have some noise over here, right? What if it just decided to make that weird shape into one of our contours? We'd be kind of screwed. So now that we have just these points, we can do a lot more mathematical tricks to just figure out what it is. So first of all, if it's not 4 points, it's not a rectangle. Throw it out immediately, because it's going to be probably one of those other masses in the image. We don't need that. We only want the rectangle. So we keep 4 points. So what else is in a rectangle? Like, what are the properties of a rectangle?
Straight edges.
Yes, so what does that mean in terms of angles?
90-degree angle.
90-degree angles, yeah. So these can just be considered vectors, and you can use the dot product to find the cosine of the angle between them. Are you guys familiar with that formula? It's just, so if you have vectors u and v, then u dot v equals magnitude of u times magnitude of v times cos theta. So dot product is easy to compute between two things. You just element-wise multiply and then add up all of those numbers. that gives you that. These are also easy to compute. You just figure out how long these vectors are, the magnitude, and now you can isolate cosine theta. And if you isolate cosine theta, what should cosine theta be if it's a right angle?
0.
Yeah, so if it's close to 0, you have right angle. If it's really far from 0, then you don't. And you'll just come up with a threshold on it and just write an if statement that says throw it away if it's not good enough for you, depending on how accurate you need it to be. So, any questions so far on what we've done? Do you have a question? Oh, okay. So, where are we now? We have 4 points. We've confirmed, so it's a polygon. We have the 4 points. We've confirmed that it's at 90-degree angles to each other. What do we do now?
Wait, why don't we find also the polygon of the shape within?
We do. I only showed the work for one of them, but you'll want to find the polygon for both this guy and the whole big thing. Yep.
Would we have to check to see that there is a rectangle inside a rectangle?
Yes. So how would you do that? If you have these 4 points, what would be the way to check that a rectangle is inside another one?
You see the points inside, which you didn't show, are within the points outside.
Yes. So I just wrote a simple function that just checks the points of one rectangle on another rectangle and returns true if one's contained in the other, and I can just use that in my checks to figure out if there's a rectangle inside a rectangle.
Did you ever get it where there was 2 of those because of noise?
No. It was very good. That was very good at cleaning it out. Because this is so wide. It's hard to have something like this. And the good thing is, so what happens if you move really far away? Like, let's say, pretend this is moving super far away.
So a rectangle within a rectangle.
It's still a rectangle within a rectangle, and on top of that, the ratio of the area of the inner one to the outer one is the same. And you have the 4 points of the corners, so it's trivial to calculate the area. You just figure out the width and height and multiply the two. And once you have the area of the rectangle, you can figure out what's the ratio of the area of one to the area of the other, and this is always going to be the same. The tape is a constant width, and no matter how far apart, how far away you are, everything grows proportionally. So when you're moving close and far away, so the ratio of this will not change. Does that make sense to everyone? Any confusion?
So then you just find the area inside and you.
Yeah. And conveniently, OpenCV also has a contour area function in which you just give it points, and it'll tell you what the area of the space enclosed by those points are.
And then after that, how do you use what equation or proportion do you use to determine how to equate that to how far something is?
So that's the next step. But first of all, we need to make sure that we've actually isolated the rectangle. If we haven't isolated the rectangle, we'll be screwed at the next step. We'll have no idea what's happening because we'll have rectangles that maybe aren't even inside each other, or they're not the right ones, etc. So what do we have now? We have a rectangle and a rectangle inside that one. We know that there's 2 rectangles, and we know that they have the correct area ratio that we expected. We know that another thing you can check is that the ratio of the width to the height is accurate, is what we expected, because no matter how far away you are, it's not going to change. It's always going to be the same ratio. So given that we know how big this rectangle is, because we know what we're looking for, we'll know what this is supposed to be. So we can narrow down very accurately that we have the right rectangle. So is everyone convinced of what we've done so far? Thumbs up if you are. Yannon? Okay, and Ari? Okay. I just want to check that everyone understands, because this can be very confusing if you get lost early into the process and then you just see random white squiggles on the screen afterwards. So, okay. Now we've isolated the rectangle. We know it's our rectangle. We have the points. What do we do next? Any ideas?
Put it there.
Of what? The rectangles?
the outer rectangle.
Okay, and what do you do with that?
We compare that to a baseline. See how
So,
much they're going to shrink.
so what's your baseline?
There should be a spec given as a competition that says how big this is supposed to be.
Yeah, so we know how big it is physically. So it's in this example, it's 24 inches by 18 inches. But
We know we can like I guess could you go before and see how many pixels wide it is at a certain distance?
yes, exactly. That's what you want to do because just in general, getting a single point and relying on everything to work on that one point being accurate is a dangerous idea. So what you would want to do is you would. So this is why I actually have this calibration. Actually, I don't know why I stood up. I have all this calibration data for that exact reason. Let me go load it again. So I took a picture of the rectangle. This is the one we're playing with, 81 inches. It's 81 inches away. I know that for a fact because I measured it with a measuring tape myself, and it's not perfectly accurate. It's probably within an inch accurate, but that's not the only point I have. I have at 164, and that's my dad, 164 inches. So I have a picture of the rectangle here, and it's much farther away. And I have an even further away one at 251 inches. So now I know a couple of points, and I actually collected a lot more than that. They're just not on GitHub for whatever reason. But so we have a bunch of images, and we know for a fact how far away they are because we can physically measure them, and then we can use OpenCV to figure out what the size of these rectangles are as a series of 4 points. So now we know how big it is in pixels, and we know how big it is in real life, and we know how far away we are. So what would we do with this?
Just fit that into a function.
Yeah, so now alright, so now we just need a what is it? So we'll get some data, and we'll probably want to do it on both the width and the height for some redundancy and make sure that we have a little bit better accuracy. So we'll get some data. And we'll fit a line to it using least squares and do the same thing here, whatever it is. And now we just have a function that we can say, all right, I know how many pixels wide my rectangle is. Tell me what the distance is. And it's just a linear function that you input it into, and it tells you how far away the rectangle is.
Is it really that varied?
No, not that bad. It's not even close, actually. It's pretty good. Given that we spent so much time on making sure that we have good threshold values, our canny edge detector is as not aggressive as possible to make sure we find the rectangles but no noise. We made sure that the rectangle is contained in another rectangle, it has the right area, it has 4 points, they're all 90-degree angles, everything is like really filtered. At this point, we have very little noise. So we went from a really noisy picture like this. From a computer perspective, this is just a jumbled mess of numbers, but we just distilled it down into a couple of points, and these points are often found without any, most of the time because of the containing rectangles check, it's found without any other noise.
Do you want that big light source right up there?
Yes, that's exactly why I took the picture at this angle. Because I wanted to make sure that the light didn't mess it up. So the light could possibly be green. I don't control the competition field in that robotics competition. I had no idea what the light would be like. I knew there might be bright lights everywhere, but it's not a containing rectangle, most likely. If it is, then fine, for a second we're kind of messed up, but can reposition and try to get it out of your field of view. Because here we're fixed to this image, but in real life we're not. So we have a little bit more flexibility. But there's all sorts of light sources here. There's this thing. There's like the reflection of the green on the table. That messed it up a little bit. Sometimes there's more windows here. There's a light source up there. There's so much random stuff in here going on. But that's why I designed all of those checks one after the other. Like it might have sounded like once we got the contour, okay, we're good. Let's find the distance. But no, we want to do a polygon check. But even then, no, we need to do four corners check. We need to do a 90-degree angle check. You do a lot of different checks just to filter out noise. And oftentimes in doing this is basically 2D signal processing, because a lot of signal processing is of time series signals that are like audio or like I don't know that many examples, but maybe sonar data, which is also audio. But all of those kinds of things would just be a single thing that you get from your measurements like that, and then you find peaks in it or whatever else you're looking for. In this case, all we're doing is two-dimensional signal processing. We have 2D instead of 1D signal, where we have two dimensions, width and height, and we will have to filter out noise. That is the biggest problem in signal processing in computer vision, filtering out noise. So to answer your question more succinctly also, is that all those checks are built in to make sure that we found the rectangle and not something else. And this took weeks of trial and error to figure out what do we actually need to filter out, what do we not need to worry about, etc. So, yep.
The functions there, those were generated by like you testing them.
Yes, so I took all these photos at different positions and I physically measured to make sure that I knew how far away it was. And then I ran it through my OpenCV code and I found those, okay, it's not on the whiteboard anymore, but the 4 points of the rectangle, and calculated the width and height of the rectangle. And then I put that on my plot, and then I did it again for another image and another image and another image. And then once I have all those points, then you can just fit a line to it. Or if it happens not to be a line for whatever thing you're doing, choose the appropriate function to fit to it. In this case, it was a line, because everything here is linear.
So it would be like a different function if you started doing like angles of different angles.
Yes. And in the next, we had 20 more minutes left, so one more thing I'll show you is how to figure out the angle. And that's important, obviously, because if your robot it can see the basketball hoop over there, but it's pointed kind of this way, and it shoots and it just like hits you instead of going into the hoop, that's not going to make any sense. Yeah, we threw it at the right speed, but that doesn't mean that it's going in the right direction. So we care where we're actually aiming it. And so in that case, it's not linear necessarily, because angles get into all sorts of trig functions that are definitely not linear. So what do you think you could do now? Now that you have, for example, this image, what could you do to find let me just zoom in. What could you do to this image to find the angle? You already know the 4 points of the rectangle and the 4 points of the interior rectangle, because we already did all that number crunching.
To find the angle of what?
So we want to find the angle, like if I'm pointing this way, but the target is over there, it might still be in my field of view because I might be able to see this much, but I want to know that I'm not pointing in the right direction. I need to move a little bit so that I'm actually straight on to the goal and I can make it in with my robot.
Compare the sides of the two sizes of the rectangle, and if they're different, and then adjust till they're equal.
So that would work for very, very extreme angles, because then it'll actually start to distort the image. But for things like 5-10 degrees, like if I'm looking at Yannin, but the basketball hoop is where you're sitting, then it's a very small distortion. It won't be noticeable, and I'll hit Yannin instead of making it into the hoop that's sitting where you are.
Get the middle point and make sure that's within a certain range.
Yes, that's exactly what you do. So if you get the center of this and compare it to the center of the image, So the center of image is right here, but the center of the rectangle is right there. So in this case, it's pretty straight on. It's right in the middle. They have the same x coordinate. So I'm basically in the middle. That's fine. How about how high they are in this angle? This angle is called the, at least what I called it was this angle was the azimuth, and this angle was the tilt. That's just a terminology. You can name it whatever you want.
Same thing once you move x, you just do the same thing to
With y.
with
Yeah.
this.
So the middle of the image is right here, but this thing is all the way up there. So you, in your image, you have this point and this point. This is the center, and this is the rectangle center. What do I do now to actually find the angle? So note that my robot is here, and it's has a camera looking here, right? So the line that the camera is pointed in, that direction, that's where the center is. And the rectangle's up here. Any?
You just use trig.
Yes. So, oops, that's not even a line. Okay, that's a triangle. That's a right angle. You know the distance to the rectangle, you can find this angle. And you know how high it is because it's fixed on a wall. You can just look up the competition specs. In this case, it's just sitting on this table, but in competition, it's on a wall. So you know this height, you know this distance. You just do tan theta equals h over d. And that's not linear, of course, but you can also fit points to this if you need more accuracy, but that works pretty well. So any questions on that? Okay, so we've now basically found the target. So I kind of just wanted to show you what the competition entailed, just so you see what an application of this is.
Welcome to the 2012 First Robotics Competition and this year's game, Rebound Rumble.
It's a very cheesy animation,
Rebound
but
Rumble is played on a 27 by 54-foot court. Alliances of 3 teams each operate their robots from behind alliance walls at the ends of the court. 4 scoring hoops are located in each alliance wall, positioned at 3 different heights. A low barrier extends across the middle of the field. 3 bridges cross over the barrier. Each bridge has 3 positions, tilted toward either end of the field, or balanced, level, and stable on the central barrier. Rebound Rumble is played with compact foam basketballs. The objective is to score as many basketballs as possible in the hoops at the far end of the court. The higher the hoop, the more points it's worth. Robots can track the reflective vision targets above each hoop. This allows them to target hoops from anywhere on the court. The match begins with each robot touching their key at the far end of the court. Robots can be preloaded with 1 or 2 basketballs each. A 15-second hybrid period starts the match. During hybrid, robots can score basketballs using pre-programmed instructions. Every basket scored during this period gets a 3-point bonus. During the hybrid period, one alliance player can command their robot by signaling to their Kinect motion sensor. At the end of this period,
that was a
human
gimmick,
drivers
and no
step
one
forward
actually
to
did
take
it.
the controls.
The Connect thing.
As the teleoperated
But-
period starts, teams command their robots to score as quickly as they can. Balls can be scored from anywhere on the court. The top of the key is a safe zone. Robots shooting from here are protected from interference by their opponents. But robots not touching this safe zone have to deal with defending opponent robots. As balls are scored, they are returned by players at the corners of the court. Robots can only hold 3 balls at a time. Once full, they drive the length of the court to score. They can use the bridge or cross the barrier to get there. Near the end of the match, robots drive onto their bridge and balance it for bonus points. 2 robots on their own bridge will get even more points. Each bridge can fit up to 3 robots, but it will be a tight squeeze to get them all on there. Roll. In qualification matches, both alliances earn cooperation points if they work together to have red and blue robots balance on the center bridge. This is critical for the team's tournament seeding position. Cooperating will be just as important as winning if you want to be successful. Good luck, and we'll see you at the competitions.
I forgot how cheesy those videos were.
Yes, they're very cheesy. But as you can see, there's all sorts of challenges put in there for vision stuff. And just trying to navigate a field on a moving robot with 4 of these vision targets all in one place while everything is happening is pretty difficult. So all of this comes together when you can make it so that someone trying to drive a robot, all they have to do is hit a button and it just shoots for them by finding the rectangle, computing the angle, computing the distance, positioning the robot appropriately, starting the motors, and shooting.
What's your accuracy?
It was, so the distance calculation was within a millimeter accurate because of how much ridiculously many pictures I took and points that I put into that least squares. It was super accurate, but it made it in about 3/4 of the time automatically. So hit the button and you have a 3/4 chance that it'll just go in without you doing anything. So
That's nice.
yeah, it's very good, and you can do it just from. We started from basic principles. You just have a bunch of numbers, and you have to try to find some useful ways to manipulate it, and that's basically what signal processing is. So any questions about classical computer vision? That's what I've been going through so far. Yep.
So this pattern of taking images and like interpreting them, that's kind of my question, but that's like basically the same thing throughout computer vision.
So in computer vision, there are a couple of major things that you would want to do. There's image segmentation, which is breaking up an image and trying to find where in the image your thing is. So that's one thing you can do. I didn't show that in this example because we didn't really need it. There's object detection, in which there could be a variety of different types of objects you're trying to detect, and you just get a picture and the operator of the computer asks what is in here, and the program has to tell them what's in there. That's a very, very hard task to do. And there are a couple of other things like, let's see, facial recognition is one. So in that case, you would be looking for things like eyes and other facial features. So classical computer vision is very, very hard because what you have to do is you have to sit there and you have to figure out how to narrow it down to the right parts of the image and calculate what you want out of the image yourself. That's very hard to do. Classical computer vision has lots of that and makes all sorts of different heuristics and algorithms in order to do this more easily, but it's not how, in the last couple of years, this is not how it's done anymore. This is very important. These are very important basics to understand and be able to manipulate images this way. But in the end, what you'll probably do is, I don't know if you guys went to the machine learning workshop, but most likely you'll just train a neural network to do this. And what it would essentially be doing is that each layer of the neural network will learn to do one of these steps. Not exactly, but something of that form. If you start dumping out what happens at each layer of a really, really big neural network that's designed after the human brain and all sorts of other fancy buzzwords like that, what it's really doing is these kinds of tasks, and it's just learning how to do it instead of you telling it. And in the end, these are the real principles behind all of that stuff. Even if they're using machine learning and big data and deep neural networks and all those buzzwords and everything, this is what's happening.
I just see the titles open tech talk nowadays. Buzzword, this
Yeah,
word,
it's just buzzword after buzzword. So that's this is the technology behind the buzzwords.
Thank you for the workshop, dude.
So if you guys are interested in just computer vision stuff, OpenCV, we went through, seeing more detail about this code, you can email me at tpankaj@berkeley.edu. I'll just write it really big because spelling.
Put out the Guy?
You can also email me there. There's that, and there's c-guy@csua.berkeley.edu. That's an alias for fun, but they both work, and they'll go to the same place. If cguy@csua is easy to remember, then that works too. It doesn't involve spelling my last name. But yeah, you can contact me and ask me about computer vision stuff. You can ask me about my research does actually end up not using any of this and just doing the deep neural network stuff. But that's only because after you get to much more complicated stuff than this rectangle business, then it's just impossible to do it by hand. You have to have a computer figure it out on its own because it's too complicated otherwise. So my research is in autonomous driving. So I'm trying to get it to get the car to take video streams and figure out how to drive from there. So we train it by driving around Berkeley all the time with cameras on our car and driving it, and it records all of our steering movements as positions on the steering wheel at any given time. And then we train our big neural networks to figure out, if I see this image, what should I do for the steering? And in the end, the layers of the neural network end up doing very similar tasks to this. It's just that I didn't have to tell it, you do this task, then do this task, then do this task. It figured it out on its own.
Who are you working with on that?
Carl Zipser. Yeah, it's in the Berkeley Deep Drive lab. So that's like what the state of the art computer vision stuff is. But this classical computer vision is super important to just understand what's going on, because if you just train a big black box and it goes wrong, you won't really understand like how it's going wrong, what's wrong with it, what can you do to fix it. Understanding the challenges behind these really complicated operations like doing thresholding and then edge detection and all of those kinds of things, that will, if you get into computer vision type stuff, that'll just help you understand that. There's actually a relevant XKCD that, if you want to see it, I can show you. Yeah, when a user takes a photo, the app should check whether they're in a national park. Okay, that's easy. You just check your GPS, and the photo, and it should check whether the photo is of a bird. I'll need a research team in 5 years. It's very hard to know if a photo is of a bird, but if you, I mean, imagine doing that with these techniques. It would be so difficult. But if you used something much more complicated, like a neural network, then it will be able to figure out what it needs to do to find out what a bird is and what a bird isn't. And that's why we don't do it by hand, because it'll be really, really hard. All right, that's the end.
Thank you very much.